Welcome back to the second part of TRIACs and their dirty secrets, where I want to go through all the stuff in the datasheets about a TRIAC. It's a bit crowded here at the moment. What I'm trying to do is expose my poor little TRIAC to a very sharp and high voltage pulse. Unfortunately, it's not cooperating. So what I have here is my power supply. It's going into some lamps with a big switch. Yeah, my electronic load. And from there, it's going into the primary of a big transformer and back into my power supply. And the transformer is just acting as a big inductor here. So you probably know what happens if I break the circuit. I will have a very high voltage spike across the inductor. And that voltage spike is going directly to main terminal 1 and main terminal 2 of my TRIAC. And so, yeah, let's have a look at that spike here. So that spike was almost 300 volts and it happened in far below 1 microsecond. Or we can actually look at it, within 200 nanoseconds. And yeah, my little TRIAC is unfazed by it, which is a wee bit odd. I mean, I can remove the TRIAC just to see if there's any difference. I have it now in my hands. Try that again. Yeah, and the spike looks exactly the same with or without TRIAC. Okay, this time I have only 250 volts. Yeah, okay. Back to the drawing board. So I wanted to demonstrate the effect of this parameter here. Rate of rise of off-state voltage. Quite a mouthful. And this is given in volts per microsecond. Yeah, typical value 50, so 50 volts per microsecond. And it basically describes how fast you can increase the voltage between main terminal 2 and main terminal 1, being in the off state, before the TRIAC switches on all by itself, without supplying any current to the gate, simply by rising the voltage across it fast enough. Obviously, I failed. And if we look at the conditions, we might deduce why. So the maximum voltage we should reach is 536 volts. My junction temperature should be at its absolute maximum of 125 degrees Celsius. And yeah, these 536 volts are about 67% of the maximum voltage the TRIAC can handle at all, and I should have used an exponential waveform. Yeah, gate open circuit, I had that, no problem. That was my little test circuit. The TRIAC directly connected across my big inductivity, the transformer. Gate floating, oscilloscope probe was connected here and here near the TRIAC. And I simply used the inductivity via that circuit here to create a big voltage spike. Yeah, saturating it and then breaking the circuit, and I had my 300 volts peak to peak across the TRIAC with a very sharp peak within 0.2 microseconds. That's 1500 volts per microsecond, so very sharp. However, my junction temperature was only 25 degrees Celsius, and the parameter was given for 125 degrees C, and for a pulse that looks more like that. So exponentially rising over, a little over 11 microseconds and reaching 536 volts. And I speculate the reason it didn't work was my pulse was simply too short. You remember in part 1, we saw that a TRIAC needs a minimum time to switch on, to get conductive. And 0.2 microseconds was obviously not long enough. My junctions were too cold, and obviously I hadn't have enough total voltage to get that thing going. Moving on. Fortunately, there are two parameters which are easier to measure. First, the on-state voltage. So if your TRIAC is in its on-state and you have a certain current going through it, of course you have a voltage drop across your main terminals. And the typical values here for current of 20 amps, I can't produce that, are 1.2 volts, respectively maximum value of 1.6 volts. Also, if a TRIAC is off and you have a voltage across it, it still conducts a little bit of a leakage current. The so-called off-state current. So typical 0.1 milliamps, that's not nothing, and maximum 0.5 milliamps. So we're not talking here about microamps. We're talking here about a few hundred microamps for that type. Let's try to measure that. We're back to our basic circuit from part 1. So the TRIAC is now switching between its terminals, that load, which is supplied by this voltage source here, and I'm measuring the voltage between the main terminals, which is now 0.792 volts. And my TRIAC is getting quite toasty at 1.7 amps. So let's turn that down, and the voltage drop goes down accordingly. It's still conducting, so it's still in the on state. But the voltage drop is seemingly proportional to the current that is flowing. I tuned down the voltage quite a bit, and now we are measuring the current through main terminal 1 and main terminal 2, just in the milliamp range. And I switch off the TRIAC. And now I turn up the voltage, and we see basically, nothing. Even on the microamp range, nothing happening here. So, and we are at 24 volts. So, just as a reminder, this is the circuit I was using just now from part 1. I measured the voltage between main terminal 2 and main terminal 1 with the circuit closed and the TRIAC on. And I measured the current through main terminal 2 with the TRIAC off. And the values for the on-state voltage, so the voltage drop across the thing, was 0.7 volts at 1.7 amps. And they say typically at 20 amps, 1.2 volts, maximum 1.6 volts. I was not really able to measure any off-state current with my 24 volt supply. It must be below 0.1 microamps. And they say at 800 volts and running the thing hot at 125 degrees Celsius, it's typical 0.1 milliamps. But it always, there is a figure here for the on-state voltage. Let's have a look at that. And there's quite a lot of information in that diagram. So on the bottom we have the on-state voltage between 0 and 3 volts. And here on the y-axis we have the current through the terminals, IT, in amps from 0 to 50. Now, that TRIAC is only specified for a continuous current of 60 amps RMS, but it can take quite some peaks. Yeah, and then we have three curves. Curve 1 is for a junction temperature of 125 degrees C, typical values. And you see that ranges from 0.6 volts up to, when we turn up the current to 50 amps, 1.7 volts. Then we have the maximum values also for running the thing hot in the curve 2. I won't read them out to you. And the maximum values if we run the thing cold. That curve here. So, and you remember when I stated varying the current through that thing, that the voltage drop across it was almost linear. And we see that here in the curves. These curves are not really like diode curves. They are quite linear. And that's what expressed in that value, the RS. Basically, you can describe that curve here. That's the curve, if we forgot the bottom end here, of a resistor. So for a certain current, I, you have a voltage drop V. It's that simple. R equals V over I. And the value for this, let's say, virtual resistance is 0.018 ohms. Now the problem is these curves go not through zero, like it would, this would be the curve of a resistor, would go through zero. But instead they start with a little offset here to the left, and that offset is given by the voltage V0 or VO of 1.195 volts. And the that's basically here, approximately. So if you don't want to go to that diagram, you can use these two values. You simply calculate the voltage drop across this virtual resistance and add that VO voltage to it, and you get you know what I mean. You can calculate directly the voltage drop you have across the whole thing. And this is obviously calculated or approximated for the maximum value curve at 125 degrees C. Moving on to the next set of values, the limiting values. You shouldn't exceed these or you might destroy your TRIAC. This will be more or less a theoretical discussion because I don't intend to destroy my TRIAC and I would be hard pressed to exceed some of these values without blowing the fuse of my main power supply. But we will return to more practical aspects later, I promise. First, we have the repetitive peak off-state voltage. That's the voltage you can put across the terminals of the TRIAC without blowing it up. Peak. So it's a peak voltage, not the RMS voltage. So when your mains voltage, like here in Europe, is 230 volts, you have to multiply it by the factor of square root of 2. That gives us here in Europe 400 volts, and yeah, we are safe. And we have even a reserve factor of 2, which we might need if we have some inductive spikes. Then there is this time RMS on state current. Since it's RMS, it's given for full sine wave and it's 16 amps. And usually our circuits here in Europe are fused with 16 amps. So yeah. However, this is given for the mounting back temperature below 99 degrees C. So you have to keep the back of your TRIAC below that temperature for you being able to really let that current flow through the thing. And there are 3 different figures given in addition. The first figure shows you the RMS current you can pass through the thing in relation to the surge duration. RMS current, so sine wave, and yeah, they specified 50 Hertz and the mounting base being kept below 99 degrees Celsius. And you can imagine that figure extended here to infinity. So if you would just run continuously 16 amps RMS through that thing, you are okay. Yeah, that's a maximum number that was given. However, if you have a shorter surge duration, yeah, the wording is what it is, of 10 to the power of minus 1 seconds, so 0.1 seconds, you can pass much more current through it. Let's say that's 28 amps RMS. So what that means is you can run the thing for 5 cycles, yeah, 50 Hertz, 50 cycles per second, in 0.1 second, 5 cycles. You can run that thing for full 5 cycles with 28 amps RMS. Then you have to put in a cool down period, which should be much, much longer than the 0.1 seconds. And then you can do it again. For 0.1 seconds, pass 28 amps RMS through it. The second figure is a little bit more simpler to read. You remember our mounting base has to be at 99 degrees C, so we can pass through the 16 amps of RMS current. And here, yeah, you're just shown how fast that is degrading. So as soon as you hit 125 degrees C on your mounting base, you cannot pass any current anymore through that thing without destroying it. Yeah, and even at 100 degrees Celsius, we are down to 15 amps. So yeah, surpassing that mounting base temperature is a very, very bad idea. The third figure is a little bit more complex again. So at the bottom we have the RMS current going through the terminals, and you see all the curves, they end at the maximum allowed 16 amps. Here we have the power dissipation caused by that current between 0 and 25 watts. And on this side we have the related maximum allowed mounting base temperature. And this scale is upside down. So 95 degrees C at the top and 125 at the bottom, which makes sense. Yeah, the more power you have to dissipate, the colder your mounting base has to be. And there are different curves giving for different conducting angles. And a conducting angle of 180 degrees basically means you are passing through full sine waves. And for example, 90 degrees means you are passing through only half of every half wave. And I won't go into the form factor here. The definition is down here. It has something to do with the power dissipation depending on the current and the voltage drop across the terminals. And we've seen the voltage drop across the terminals is kind of a linear function, yeah, with a little offset. But that would require a little bit too much math to go in there. So anyway, for a conducting angle of 180 degrees at 16 amps, so full sine wave 60 amps, we are exactly at our maximum allowed 99 degrees C. If we would pass only half of each half wave through the device, we would be here at a conducting angle of 90 degrees, and we would be allowed to run the thing, at least the mounting base, a little bit higher. So let's say 105 degrees. And so forth. And as you decrease your RMS current, of course, you are allowed to run the thing hotter and hotter and hotter. And at 0 amps, you are allowed to heat up the mounting base to 125 degrees C, which is, I think, incidentally, the temperature at which your junctions would be destroyed. Now, if you think that was heavy, wait for the non-repetitive peak on-state current. So that's the peak current the device can take on, but not repetitive. And this is basically expressed by that condition that your initial junction temperature before applying such a current needs to be 25 degrees C. So 25 degrees C means room temperature. The thing has to be cold. And there are two values given here, one for 20 milliseconds, that's incidentally for 50 Hertz, if you think about it, and for 60.7 milliseconds, that's incidentally for 60 Hertz sine waves. And that peak is a full sine wave, I mean 1 full sine wave. Only one cycle passed through the device with that current here. And of course, we have some figures. The first graphic shows you how much peak current you are allowed to pass through the terminals in relation to how many cycles you intend to do that. I mean, the number of cycles at 50 Hertz, you can translate that easily into time. So one cycle is 20 milliseconds, two cycles 40, 10, 200 milliseconds, 100 cycles 2 seconds, and 1000 cycles 20 seconds. And you can translate the peak current of the sine wave, of course, into an RMS current. So if we only pass one cycle through it, that is for 20 millisecond RMS current of 130 amps or peak 155 amps, that's exactly the value that was given in the datasheet for 50 Hertz. If we do that for 10 cycles, so for 200 milliseconds, we have to notch that down to a little above 80 amps peak or 57 amps RMS. And as we continue the number of cycles, we would end here, and unfortunately the legend is put over here, but we should end somewhere here at 16 amps RMS at the end of the curve. And that is, you remember what you're allowed to put through the TRIAC continuously. The second figure for that parameter is even more esoteric. This time we are talking really about a single pulse through the terminals in form of one full cycle of a sine wave, nothing more. And we're talking about the duration or frequency of that pulse, which is given down here. So the scale here originally is in milliseconds, and that's should be a small TP, not a capital TP, typo in a datasheet. It happens. And it goes from 10 to the power of -2 milliseconds to 10 to the power of 2 seconds. Or in hertz, from 100 kilohertz to, here we are, the curve ends at 50 hertz. And that scale here is again the peak amplitude of the sine wave in amps. So we are basically here looking in the diagram from very short pulses of that form of 0.01 milliseconds to 50 hertz pulses in that sinus form of 20 milliseconds. And the curves show you how much peak current you are allowed with one single pulse to put through the device. And we have here two curves. Let's start from here. So the longer your pulse goes, the less peak current is allowed. And at 50 hertz about here, this is the allowed peak current of 155 amps we've seen as number. If the pulse goes shorter, you are allowed to put in a lot more current. So this is, I don't know, 500 amps. But as the pulses get even shorter, this sharply drops out down again. And there we have a separation. We have a general curve here, which refers for the so-called DLT-DT limit. We will talk about that in a second. And we have a curve here that is even lower. So at 100 kilohertz, your peak current is, let's say allowed 15 amps if one of these half cycles is operating in the fourth quadrant. Terminal 2 negative, gate positive. Here, you saw it in part 1, the fourth quadrant of a TRIAC works not so well. Let's move on. And we skip that I squared t parameter for the moment and go right to the rate of rise of on-state current, dit over dt, where we have here 4 values, and talking about typos in datasheets, these are the conditions for our 4 quadrants. And you see in quadrant 1, 2, and 3, we apply a gate current of 20 milliamps. And in quadrant 4, you know it, we need to apply more gate current. In this case, 50 milliamps. And the value is given in amps per microsecond. And for the first 3 quadrants, we are allowed to increase the current when switching on the TRIAC by 50 amps per microsecond. And in quadrant 4, we are only allowed to increase it by 10 amps per microsecond. You see, if we operate in quadrant 4, our allowed limit, peak current, the higher the frequency got of our pulse, the lower it was, much lower than for the other quadrants. We skipped that parameter, I squared t, for fusing, and as it says, that's for selecting the right fuse for the TRIAC. And you find that parameter also in the datasheet for fuses. I squared t, amps squared per second. And that's basically an energy. So I squared times R of the fuse, which is given here, gives you a certain power, or the power loss of the fuse when a certain current goes through it. Now multiply that by time and you get an energy. And the time scale we are talking here is, in that case, 10 milliseconds. And simply when you select the fuse, look into the datasheet of the fuse for a value not bigger than that, because otherwise, if there's a sharp spike in current, your TRIAC might fuse instead, of your fuse. Peak gate current and peak gate power. Of course, we cannot put an arbitrary amount of current into our gate. It's limited here to 2 amps. And we cannot have an arbitrary high power loss across our gate. It's limited to 5 watts. And the power loss, of course, is calculated by the current through the gate by the voltage drop across the gate. And to have 5 watts dissipated in the gate at 2 amps, we would need a voltage drop across the gate of 2.5 volts. With that TRIAC, we will never or should never reach these 2.5 volts, because if you remember, the maximum gate trigger voltage, that is the voltage across the gate at 25 degrees C, was 1 volt. However, we have also that temperature curve here that gives us the relative gate trigger voltage across the temperature range. And you see at very low temperatures we will have to multiply that 1 volt by a factor of 1.2. That still leaves us with 1.2 volts, so less than half than the 2.4 volts we would need to dissipate 5 watts. Now, these are peak values, and there are no additional conditions here given for what's meant by peak here. For that, we would have to look at a typical application. So let's assume we have a load on an AC source, maybe mains AC, switched through a TRIAC. And the gate of the TRIAC we can control by an opto TRIAC. Yeah, there are TRIACs so you can switch on by light. And the gate current is limited by a little resistor here. Now, if we run that thing at a 50% duty cycle, we would have to switch on the TRIAC exactly at 90 degrees or 270 degrees of the sine wave. That is exactly when we are at the peak voltage of our AC. That's for mains AC in Europe, 400 volts. Now let's have just a look at that moment where we switch on, shortly before and shortly after. So the voltage drop across our load while we are off is of course 0. Then the TRIAC within 2 microseconds, typical, our type here, switches on, so the current starts to flow and we have a voltage drop that finally reaches our peak voltage, and then it follows the normal voltage drop of our sine wave. Accordingly, the voltage drop across the TRIAC is the mirror of that. While the TRIAC is off, all the voltage of the sine wave is dropped across the TRIAC. So we have here the last portion of the sine wave increasing. And then as the TRIAC gradually switches on, the voltage drop across it goes almost, not completely, almost down to 0. Now, what does that mean for our gate current? Our gate current, initially, that little resistor here, and we forget the voltage drop of 1 or 2 volts across here between the gate and the main terminal 1. It sees the peak voltage of the AC. Again, 400 volts in Europe. That is, we have a huge spike here. And that spike then goes down while the TRIAC switches on, and we build up a voltage drop here across our load resistor. And it's these kinds of spikes peak gate current and peak gate power is about. The average gate power is given for a period of 20 milliseconds, which corresponds again with 50 Hertz, and it's 0.5 watts. We already looked up here that the voltage drop across the gate is at a maximum of 1.2 2 volts, let's say 1.25 volts, that's easier to calculate. So these 0.5 watts would correspond to a constant current of 400 milliamps to the gate. And that's more for circuits like that, where we can actually control the gate current independently from our load voltage. Well, storage temperature minus 40 degrees C to 150 degrees C, so don't cool it down with dry ice and don't put it in the oven. And more importantly, the maximum junction temperature, 125 degrees C. We've seen that junction temperature pop up in different diagrams. For example, that one, where all the curves end at 125 degrees Celsius. Beyond that, yeah, end of the road. And that brings us to our final set of parameters, the thermal characteristics, which are, yeah, the same for all semiconductors. So first we have here the thermal resistance from junction to mounting base. So, yeah, the metal back of the TRIAC. And we have the thermal resistance from junction to ambient free air. Like when you're running that thing without any heat sink, just, yeah, for example, like I did it, stuck into a breadboard. Anyway, here's the next specialty for a TRIAC. Thermal resistance junction to mounting base, we have two values. We have a half cycle value and a full cycle value. And to understand that, we have to go back to our semiconductor layers. If we are in the first half of a sine wave, the current will go in one direction through the TRIAC and the brunt of the power losses will be generated in certain junctions. Yeah, it's very asymmetric. When we are in the second half of the sine wave, the current reverses and the brunt of the power losses are generated in different junctions. That is, if you switch the TRIAC on only for, let's say, positive half waves and, yeah, cut out the negative half waves completely, you only generate heat in certain regions. And you cannot use the whole substrate of the TRIAC to transfer heat to the mounting base. Heat is only transferred from certain spots. And that's the reason that for half cycle operation, you get a higher thermal resistance from the junctions, yeah, plural, to the mounting base. Because you are really concentrating the power losses in the substrate on certain spots. While when operating it in full cycles, you are spreading or heating up the whole of the die, and so you get a little bit lower thermal resistance to the mounting base. And of course there is a figure for these parameters. Yeah, the graph is also a little bit more esoteric. On the x-axis we have a time scale giving us a pulse length. You can also say duration or length of operation. And it goes from 10 to the power of minus 5 seconds over milliseconds, seconds, 10 seconds, and extends in theory to infinity. And you see, when you operate that thing longer than half a second, then the values given in the table apply. 1.2 Kelvin per watts and 1.7 Kelvin per watts for bidirectional, that is full cycle, and unidirectional, that is half cycle operation. However, if you apply only short pulses, and here is the 20 millisecond mark, or 50 hertz, then we have only 0.4 Kelvin per watts. And that's the reason why when the thing is cold, you can put in one full sine wave for 20 milliseconds or one full 50 hertz sine wave with 155 amps, without blowing the whole thing up. But nevertheless, this is, esoteric. I wouldn't expect, if we go down here to 0.04 Kelvin per watts and go over and then put a pulse in with 0.1 milliseconds of 1550 amps, that the thing would survive that. Okay, so forget about that. If we go a little bit back, we see that many of the graphs, here's on-state current as function of surge duration and maximum RMS on-state current, are all given for a mounting base temperature of 99 degrees Celsius. So, in theory, you don't have to work with these values here, as long as you make sure that the mounting base of your TRIAC doesn't get hotter than 99 degrees Celsius. So you can simplify your thermal design and only have a look at the heatsink you are screwing at the back of your TRIAC, take the heat resistance of that, assume allowed maximum of 99 degrees Celsius on one side, and on the other side your ambient temperature, so maybe 40 degrees Celsius. We're actually through every parameter now in the datasheet. That was a whole bunch of paperwork this time. Sorry. Besides the failed experiments in high voltage spikes at the beginning. But I promised we will have a look at some practical aspects of the whole thing. And I will do that in the next and last installment of this mini-series, and then we put that guy here to use and switch some real AC for a change. Till then, bye!